Let's move on to domain 5. All right. If you think about it, folks, domain 5, that central atom has got 5 things coming off of it, which means if you are in domain 5 or domain 6, you have to be exceeding the octet rule. Like you have to be. Okay, you have to be exceeding the octet rule. Stop and think about it for a second. If you are in domain 5, that means you got 10 electrons around you, whether it's in bonds or lone pairs, and you must be exceeding the octet rule. So remember, atoms that can exceed the octet rule, they are in period 3 or below. Okay, and they can take those extra electrons and shove them into the empty d orbitals that they're not using. So let's get to it. Let's do PCl5. Here's what I want you to do. I want you to do a crappy Lewis structure. Then we're going to find it, and we're going to draw it better. Awesome. So that's 5 plus 35 equals 40. Phosphorus, 5 chlorines coming off of it, exceeding the octet rule. It's okay. Phosphorus is in period 3 or below. It's allowed to do that. Used up 10, got 30 left. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and 30. And there it is. But now, how do we draw it? Well, this is our trigonal bipyramid molecular geometry. It's beautiful. It's actually a linear and a trigonal planar 180 degrees apart. Let me show you what I'm talking about. Here we go. So here's our structure. It's got 2 groups on the top. So I'm going to remove, those are called the axial substituents. I'm going to remove the equatorials so you can see the axials. Those are the guys on the top and bottom. And then we have these, so they're 180 degrees apart, right? And they're going to be 90 degrees apart from these guys in the middle. Now I'm going to put the guys in the middle back on. So you can see how these guys on the top are 90 degrees away from the ones in the middle. Now I'm going to remove the axial groups. So here's the guys in the middle. If I flip that up, hopefully you can see how this is a trigonal planar. So around the middle, we've got a trigonal planar here with the 120 degree bond angles. So this is like a linear and a trigonal planar both together, right? It's a linear and a trigonal. So we're going to have 2 different bond angles, okay, or maybe 3, although I don't need the 180. So we got a 90 degree angle between the axial and the equatorial, and we got 120 degree bond angles in the equatorial plane. Now, how do we draw it? Well, the best way to draw it is like this, okay? Put one of the equatorials in the plane, and then that will have one of the equatorials come out at you, and one of the equatorials go away from you. So essentially, and I got the beautiful thing with the whiteboard here, okay? I can just wedge one of these guys and dash one of these guys. And now I need you to show a 90. I need you to show a 120. Okay, and you don't have to show the 180 unless you really want to. This is a trigonal bipyramid. In the biz, we call it a TBP, right? Trigonal bipyramid, right? So, you know, we call it a TBP in the biz. Domain 5, 0 lone pairs on the central atom, trigonal bipyramid. Now, everything else is going to be a modification of this. So we're going to be replacing bonding groups and popping lone pairs in different places. Okay, so let's get on that. Any questions on the trigonal bipyramid, PCl5? All right. Next up, we have my absolute favorite shape. I love this shape. We did it last time, but you won't remember, right? Because you just do so many of them. You don't, you know. Let's do SF4. I absolutely love this molecule. You'll see why. Okay, let's try to get the right Lewis structure, and then we'll talk about how to find it and draw it properly. You got this. SF4. All right, we got 6 plus 28 equals 34, which is a crazy number of electrons for a structure. You'll see why in a second. We got 4 fluorines coming off of this bad boy. That uses up 8, leaves us with, oh my goodness, 26. Here's the problem. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I still have 2 electrons left. Where do they go? Central atom, because it can exceed the octet rule. This is domain 5. We got 4 bonding groups and 1 lone pair. It's domain 5. The question becomes, of a trigonal bipyramid, what atom do we remove and replace with a lone pair? Okay, do we remove an axial and put a lone pair at the top that's 90 degrees away from 3 equatorial arms or substituents, or do we remove an equatorial bonding group and put the lone pair there? This guy is now 90 degrees from the 2 axials, and it's 120 degrees from the equatorials. Which is more stable? The answer is this. Okay, here's why. VSPER theory. Lone pairs need as much space as possible. This lone pair is able to spread out more by only being 90 to 2 things and 120 to 2 others. Now, okay, here's the thing. It's still going to distort these bond angles. So these bond angles, this is no longer 90 and it's no longer 120. It's going to be less than 90 and less than 120 because that lone pair bends everything. How do we draw it? Well, it's best to put the lone pair in the plane of the paper, okay, and then still have a bonding group coming out at you and going away from you. So something like this. So you're going to use sulfur. You're going to do your 2 axial bonding groups. We're going to put the lone pair in the plane. That'll leave a fluorine to come out at you and a fluorine to go away from you. There's our structure. What is the name? Oh, bond angles. This is now less than 90, and this is now less than 120. Oops. What's the name of this? Here's why this is my favorite, folks. You guys are going to absolutely love this. This is called Seesaw or Sawhorse. Why is it called Seesaw or Sawhorse? Boop, 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 boop. It's like a seesaw. Look at that. It's like the most adorable molecule like you have ever seen, right? Okay, you know the guy that figured this out just like had this on his desk and was just, you know, it's like, I'm gonna call this Seesaw. Okay, so yeah, there you go. Seesaw or Sawhorse. I obviously prefer the name Seesaw. Okay. All right, man, what are we up to? Let me check the list here. I don't want to make sure I'm not missing anything. So let's we just did that. Should we do ClF3? Let's do ClF3. Awesome. Let's do chlorine trifluoride for this next one. And again, if you ever have any questions, please unmute yourself. Let me know. All right, here's what I want. I want at least a crappy Lewis structure of ClF3. Give me at least a crappy Lewis structure of ClF3. What do we got here? We got 7 plus 21 is 28. Fluorine in the middle, 3 fluorines coming off of it. Used up 6, got 22. We're going to make the fluorines happy. 2, 4, 6, 8, 10, 12, 14, 16, 18. They're all happy. 20. Now the chlorine's happy. Here's the problem. Everybody satisfied the octet rule, and I still have 2 electrons left. What do you do when that happens? Shove them on the central atom. Okay, why? Because that central atom can exceed the octet rule. So now what do we have? We're in domain 5, 2 lone pairs. Domain 5, 2 lone pairs. What do we do? Well, now we take our trigonal bipyramid, and we're going to replace another one of the equatorial groups with a lone pair. And now here's the good news, okay? We can spin this around, and we don't show the wedges and dashes on the lone pairs. So we can have everything be in the plane of the paper. Now, okay, these bond angles are not going to be a pure 90. Those two lone pairs are going to bend everything, right? Kind of like that. So it's going to be less than 90 because of those two lone pairs. So best way to draw it, okay, I would actually accept this as long as you put less than 90. Now, your paper has it spun 180 degrees, and that's totally cool. Or I'm sorry, has it spun 90 degrees. So this is now less than 90, and it's T-shaped. Why is it T-shaped? Because it looks like a T, right? We could spin it, and it looks like the letter T. Cool. Awesome. Let's try the triiodide ion. So I3 minus 1. Try I3 minus 1. See if you can't get the right Lewis structure to start with. And then, see if you can't find it before we go over it. All right. So we got 21 plus 1, which is 22. We're going to have 3 iodines. That uses up 4 electrons. Oops. Which leaves me with what? 18. 2, 4, 6. That guy's happy. 8, 10. That guy's happy. 12, 14, 16. But you can see I'm still short, or I still have 2 too many. We're going to add that as an extra lone pair on that central iodine. Now, I would actually accept this the way that is drawn, okay? You don't have to spin it around. Here's what's happened. We're finally going to remove that last bonding group in the equatorial plane of the trigonal bipyramid. And now I have 3 lone pairs, okay? The 2 bonding groups make a straight line. Here's the cool news. Ready? This is like vectors in physics, okay, or net forces. I get a lone pair here. I got another lone pair here and another lone pair here. They are all a perfect 120 degrees apart. Okay, so what happens? This guy's trying to push. This guy's trying to push to get as much room as possible. This guy's trying to push to get as much room as possible. And because they're all a perfect 120 degrees apart, nobody wins. And this bond angle is actually a perfect 180 degrees. So that is a perfect 180 degrees. And it is linear. And again, you don't have to show wedges and dashes. And again, if you want to show it vertically, I mean, your paper has it drawn vertically, but that doesn't matter. It's still 180 linear. Cool. How we feeling about domain 5? We just got through domain 5. Domain 5. All right, let's do domain 6. Domain 6. Sulfur hexafluoride. Go ahead and see if you can't put it together correctly. And then see if you can't find it a while. And then we'll talk about how to draw it and all that jazz. 6 plus 42 equals 48. Sulfur in the middle. We got 6 fluorines coming off of it. That uses up 12 electrons, got 36 left. If you're a thinker, each fluorine needs 6 electrons, and you got 6 of them. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. There's your structure for SF6. But how do we draw it? Well, here it is. This is our octahedral molecular geometry. And the octahedral molecular geometry is pretty awesome. We do need 2 sets of wedges and 2 sets of dashes, though. If you look at that octahedral molecular geometry, okay, you're going to have 2 groups coming out at you, 2 groups going away from you, and everybody is 90. So let's take a look. Set my marker down. We got 2 groups coming out at you, 2 groups going away from you. So the best way to do this is to wedge the front 2 and dash the back 2. And you can show some three-dimensionality to this now. Everything in this structure is 90. So pick an FSF bond and label it 90. That's 90, that's 90, whatever you want to label. They're all 90-degree bond angles. Yes, there is a 180. You know, these two are 180, these two are 180, these two are 180, but you don't have to show that. All right. On to the next. We got two geometries left. We're not going to do the last two on that sheet. So, by the way, that was octahedral, bond angles in 90. I don't think I actually wrote down octahedral. Here's a pretty rare geometry. How about CLF5? CLF5, give that one a shot. We got 7 plus 35 equals 42. We're going to pop a chlorine in the middle. We're going to have 5 fluorines coming off of that. 1, 2, 3, 4. We're just going to put them all up here all crazy like at first. Okay, that uses up 10 electrons, leaves you with 32, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. I still got 2 left. Where are they going to go? On the central chlorine atom. Notice that we are in domain 6. We got 1, 2, 3, 4, 5, 6 things, 5 bonding groups, 1 lone pair. Domain 6, 1 lone pair. This is going to be a square pyramid. Square pyramid. Where do they come up with this name? What is going on there? Here's where the name comes from. Take your octahedral. Pick any one of them. They're all the same. Rip one off. Boom. Okay, what are you left with? Oh, I'll leave this guy with the lone pair. So my lone pair is here now. What are you left with? You are left with a square pyramid. Think about it. How do we name, if you connect all the dots, how do we name pyramids based on the shape of their base? That base is a square. You got a lone pair hanging out here. It's a square pyramid. Now, because this lone pair is down here, it's pushing up on everything. So now my bond angles are going to be less than 90. But what do we do to draw this? You're going to put a chlorine in the middle. You're going to have that lone pair on the bottom. You're going to have a fluorine on the top. And then you've got a wedged fluorine out here, a dashed fluorine, a wedged fluorine, and a dashed fluorine. If you connect all the dots, that would be a pyramid, a square pyramid. So this is a square pyramid, and my bond angles are now less than 90 degrees. So that's a pretty rare shape. Oh, I left the lone pairs off the fluorines. Tisk, tisk. There we go. Cool. All right, we got one more shape to do, and it's a pretty awesome one. You guys drew the Lewis structure for this last time, but we didn't talk about its shape. Another pretty rare shape. And a special shape because I was telling you guys about this molecule last time, xenon tetrafluoride. This was the first time they ever got a noble gas to do anything. And that was exciting. But they also got a new molecular geometry when they did this as well. And that was also exciting. It was like doubly exciting. So anyway, add up all your valence electrons. Try to get the right connectivity. See if you can't find it on the VSPER chart. Give it a shot. Good luck. All right. We got 8 plus 28 equals 36. We're going to pop xenon in the middle. We're going to have 4 fluorines coming off of it. That uses up 8, leaves me with 28. Make the fluorines happy. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We've still got 4 electrons left. Where do they go? Central xenon atom. What do we have here? Well, we're in domain 6, folks, and we got 2 lone pairs on the central atom. Domain 6, 2 lone pairs. Domain 6, 2 lone pairs. This is going to be square planar. If we look at the sheet, square planar right here. Okay, and let's talk about this shape. So now, essentially, we've got our octahedral. We removed 1 group to get to square pyramid. Now we need to remove another bonding group because the lone pairs want to have as much space as possible and be as far apart as possible. They're going to be on opposite ends of the octahedron. And what are we left with? We're left with a square, if you connect the dots, and all the atoms are in the same plane, literally square planar. There it is, pretty awesome. How do we draw it? Well, essentially, you just put the lone pairs on the top and bottom, and we're still going to double wedge for the two coming out at you, and we're going to double dash for the two going away from you, just like that xenon tetrafluoride. How we feeling, folks? How we feeling? Those are all of our shapes, man. So what do you need to know? Well, you need to know pretty much everything on this sheet. Plus, we're going to add the polar, non-polar stuff. Except for, there we go. You do not need to know this guy or this guy. Those shapes are so rare, it's not even worth it. So you really want to, memorize this. Now, if you're on limited time, then the ones that are absolutely essential to memorize would be those, what is that? 8? No, 1, 2, 3, 4, 5, 6. Yeah, 8. These 8. And then work on these 5, okay, afterwards. But I would start with those 8. Those 8 are the most important. And then the Seesaw's T-shape, that domain 5 linear, the square pyramid, and the square planar, those are all important, and you might see them on the test. Okay, but these 8 are the most important. They are the most important.